Yeah, okay. Just a second. Okay.
Right. So, Abhirup, are we okay to go ahead? Then I'll start the session.
Sure, good.
So, welcome everybody for this second talk in the afternoon session. And today it's a pleasure to introduce Professor Abhirup Datta from IIT Indore. Abhirup is an expert on a wide range of topics, especially related to observational astrophysics. And today he'll be talking about continuum imaging, the challenges related to it, both from the HPC side as well as from the science perspective of it. And it is most related to how we can obtain data from radio observatories and then image them and do science with them. So Abhirup, please go ahead.
Thanks Dipanjan. Thanks all the organizers for this particular workshop. It's been a real pleasure to be here and talk to such a diverse crowd about a topic which we are all who are doing this kind of science will be affected by. And as Girish rightly said before me, I think that we are a little bit behind, and it's a good right time to talk about all this and come to a consensus how to move forward. So if for the younger crowd who are wanted to interested in radio interferometric imaging and synthesis imaging, these are the basic takeaway. I mean, please, if you have not been yet introduced to these books, please get it one way or the other. It will help. So for the diverse crowd who are not astronomers, who are not radio astronomers, I think what we are talking about here is this is the full electromagnetic spectrum. You can see right down near the left, it is the higher, lower wavelength or higher frequency. You can see this is the optical band, which is visible from the ground. And then we are fortunate that we are in the part, the radio astronomy people who are in a part that where we can observe most of the band from the surface of the Earth. But people who are near X-ray, gamma ray, UV, they're not that much fortunate. So it has to be space-based observatories and a minor, fraction of the band in the optical. Which is visible from the surface of the Earth. Moving on, why? It's just a motivation if you are astronomer of different wavelength. I mean, science is everywhere in different parts of the electromagnetic spectrum. Often, this is a classic picture of our galaxy, observed from radio continuum 408 megahertz up to X-ray, gamma ray, and so on and so forth. So science is everywhere. So you can observe a single cosmic source in different wavelength, and you can gather information for different parts of the wavelength band. And when you put it together, you can actually make a total picture of that particular source. So different wavelength means different astrophysical processes that basically are probes to different activities which are going on in that particular source of your importance. So for example, this is a classic picture of a Crab nebula where you have different wavelength band, X-ray, optical, infrared, and radio. They all look completely different from each other. But when actually you try to understand what this source is all about, you have to understand that from the composite image which is created from the different wavelengths. This is another kind of a study. This is looking at the largest possible bound structures, galaxy clusters, in this case, the Able Southern Cluster 1063, where you are looking into the radio image from GMRT, which is here. Then you have the X-ray contours from Chandra and an optical image in the background over here. So you make the total, you understand what is going on for these clusters, because clusters are the most bounded object, the the largest massive objects you can find in the universe, and merger of two clusters kind of produce energy which has never been seen since the Big Bang. So it's a very important object to study. So again, to make the understanding clear, you have to observe in different wavelength bands. Now, something closer to my interest is cosmology with H1, as Girish pointed out clearly, so I don't have to introduce it completely. So since Big Bang, the universe expanded. Keep happening. Sorry. This is the Big Bang at the different kind of a schematic than Girish's. This is where the Big Bang, everything began, which is the kind of acceptable model currently. And here is the CMB, the last surface of last scattering. Universe kept on expanding till it became neutral and remained neutral till the first stars, first galaxies, first black holes came and reionized the universe. And what is happening is that this epoch when the universe went from being completely neutral to fully ionized, fully reionized again, where neutral fraction dropped from being 1 to 10 to the minus 3. This epoch has not been studied that well yet. And so there are a lot of experiments, including the square kilometer array, are designed to study this particular extended epoch, the last phase of the structure formation history we can study. And this has been done by using the neutral hydrogen transition, which lab frequency is 1.4 gigahertz. But as you're looking at a redshift which is much higher, it gets redshifted to frequencies less than 200 megahertz. Okay. So SKA, the low telescope, or many other telescopes like HERA, like MWA, LOFAR, are basically trying to detect the signal from this particular epoch. Even if you're talking about doing cosmology with radio astronomy, you're looking at things which are, this is all simulated, of course, because no signal has been yet detected. So if you're looking at that simulated sky, which shows you what is happening in intergalactic medium at that far redshift, you are seeing that signal coming through all the different foregrounds, the extragalactic, the galactic foregrounds, which were actually being before in my previous slides, like here, the galaxy, our galaxy, and extragalactic sources like galaxy clusters, they are being somebody's science case. But in this particular case, for our observational cosmology part, at these frequencies, these two, galactic foregrounds and extragalactic foregrounds, are completely noise for observing this faint signal from this epoch of reionization and cosmic dawn. Okay, so essentially, if you're interested in looking at H1 science from the high redshift, you have to actually get rid of all these foregrounds, and that's the challenge which we'll come to in the later part of my talk. Okay, so I tried to motivate it with few science cases that why should you do radio astronomy and why this kind of very high sensitive observations with either our upgraded GMRT or in future the SKA, the square kilometer array. Now coming to back to that same electromagnetic spectrum diagram, but in a different way now. As you're moving from the highest frequency or the lowest wavelength down to the highest wavelength or the lowest frequency, you can observe every part of the spectrum and you can make detectors to look into that particular part of the spectrum. There cannot be single detector covering the entire subbands also. So for radio also, you have to make multiple receivers to cover this entire length of the wavelengths. Now, one thing to keep in mind, just a cheat sheet, is that the resolution of a detector depends roughly on the wavelength over the size of the detector. So that becomes very important. What is resolution? Resolution means the power of a telescope to differentiate between two sources which are placed at two different parts of the sky. If a resolution is poor, you cannot differentiate between a star lying in this part of the sky to that part of the sky. So the resolution is a very important component of making a detector, and that should be remembered throughout this particular talk at least. So to keep the resolution same, if you're looking at the sky at the shorter wavelengths, you need a very small detector. And for the longer wavelength, you need a very large detector. Okay, so you can imagine that if you're looking at sky at 1 millimeter wavelength versus 1 meter wavelength, it's kind of about 10 to the power 3 kind of difference in the wavelength. But the size of detector cannot be varied from few millimeters to few meters. It is fine, but suppose you're going from few centimeters, few tens and hundreds of meters, that becomes a little bit over, overarching problem, because at some point the size of the dish you need to have, size of detector you need to have, is kind of impractical, infeasible to build. Okay, so let's keep that in mind. But people, radio astronomers, radio engineers, have not been bothered by that too much. Here are some gigantic structures which has been built so far. The starting over some 1957, the Jodrell Bank, where the SK headquarters are now. It's 76-meter dish. Then Parks, 64 to 70 meter, kind of inner one is 64, and the outer mesh goes up 70 meters. Then there's Effelsberg in Germany, right near the right end of my slide in the bottom. And then you have the Arecibo, which is 300 meters, sadly decommissioned recently. And then it took about till 2000 to build the 100-meter Green Bank telescope. But the difference between this and Arecibo is this is fully steerable. So it can point to any part of the sky, and it's 100-meter dish. Now 100-meter is a sprint, right? So this is a gigantic structure. But these two were the record holders, kind of, until recently. The China built this FAST telescope, which is 500 meters size, but effectively, instantaneously, it is effective area is kind of 300 meters or so. So, but these are still like the Arecibo or FAST, they cannot be moved. It's a huge structure. So you can imagine if you're trying to get anything bigger than this, it is not possible to make. So what do we do? So the clever technique of introducing interferometry. So you have a single dish, and now you have a synthesized, if you want to make the diameter of the dish larger, instead of making a single dish of that diameter, you break up into much smaller number of dishes and make multiple of them. Okay, and we will come to this little bit later, but so you can imagine as you're looking at one particular part of the sky and your Earth is rotating, so you are actually it appears like this entire thing is also rotating in projection. Okay, so this has an effect in the final Fourier space sensitivity. So we will come to that a little bit later. For now, let's keep it simple and say, for example, if it is just snapshot imaging, it's as if you're breaking up this entire big dish of a large diameter into much smaller dishes of smaller diameters. Okay, and that actually sorts out the problem of making it more practical as well as lower in cost and maintenance as well. I will come to this part about Earth rotation a little bit later. So how do you absorb this? So you're breaking up a bigger dish into much smaller, but so that doesn't mean that you're actually doing it in the same plane. What we're trying to do is something similar in the textbook optics we have done before, is we have all done this Young's double slit experiment. So it's kind of the same. You imagine this the two slits as these two different antennas of the smaller diameter, of course, and each pair kind of prints like a fringe in the surface on the sky. Okay, so you have one pair, you have one pattern, you have multiple such pairs from these different antenna combinations. You have n antennas, so you have NC2 combinations. So you have NC2 combination of fringes, And when that kind of is superposed on each other, you kind of get a pattern like this for the sky. So you're looking at something like this, which is a classic FR2 radio galaxy, and you're looking at that, and this is what you reconstruct by this interferometer. Okay. So more we can discuss it more later on, but that's basically the principle behind the interferometry. So in the sky plane, you have the image, and in the visibility plane, which is the Fourier domain, you have something called visibility, which are basically nothing but voltage correlations coming out from the any two pairs of the antenna. Okay, so how do we interchange? So we have reduced the impracticality of making a larger dish by making much smaller dishes. 1, it is lower in cost. 2, it is easy to maintain. 3, but the disadvantage is that there is no way you can fill the entire this hole by putting any number of such small antennas. So no matter what you do, you will not get a complete coverage. And because of this incomplete coverage in the visibility space, UV space, you have this kind of structures which are imprinted on your so-called sky as observed by the interferometer. Now we will come into the way how do we get rid of this towards the end, second half of this talk. Okay. So far, let's be at least inspired that there's a way to get out of this problem of resolution effect by going into interferometry from a single dish or single detector. Sorry, another way, just we are not covering that, is that we are assuming that a single telescope has a single receiver. Okay, so it's like a single pixel camera. Okay, however, techniques are there now to make multi-pixel camera on each antenna, and they're called something called focal plane array. But for this particular lecture, we are not going into that, so we are skipping that. So the only way you can get resolution is by doing interferometry for this particular lecture. Okay, here is a simulation. Sorry, it gets started. I have no way to stop it. So if you see, but it will keep on going back and forth. So we will go through a little bit multiple cycles of this. So what we're doing over here is just to explain what we told in the previous 2 slides, is we have a model image. It's all simulation, okay? Model image with a single source of 1 Jansky. Jansky is a unit on radio astronomy. It's 10 to the power minus 26 watts per meter square per hertz per steradian. Very faint number compared to any standard electrical devices which gives powers in milliwatts and so on and so forth. This is 10 to the power minus 26 watts, so fairly faint. So what we have over here in the top left corner is 1 Jansky source in the field center. What we have below this in the bottom left is array with different number of elements. So it will go from 2 to 3 to 4, 5, 6 to GMRTs, which is 30, and then 64, and then 128, and finally to 512, I guess. Okay. This is snapshot imaging. So single every pair of antenna is observed for just 1 timestamp. Okay. This is the corresponding UV coverage or the UV footprint in the Fourier plane. And this is the reconstructed image which is formed out of this simulation. Okay, so if you keep an eye on just the bottom right corner, you will see as the simulation progresses and number of elements gets increased, you are more able to reconstruct what we started off on the top left corner, which is a point source or a compact source. Okay, what does it mean? It exactly means what we discussed in the previous slides, that as we kind of fill up the dish. So as we fill up this particular dish diameter mentioned in green by the smaller number of telescopes, smaller size telescopes, more number of them, we will be coming close to what we would have gotten by a single dish. Okay, the resolution wise. So same thing is clear as the number of elements goes from 2 to 512, you will see that you are able to reconstruct the image, the model source completely. Okay, let's move on because we're a little bit behind in time. So just to explain that this is the same principle. So they have two antennas separated by a distance of B, which is called baseline in our terminology, but that's okay. And you are basically collecting them and correlating them. Okay, so that's the voltage coming out of that. So we will have one complex voltage correlation from every pair of antenna. So you have n number of antennas. You have NC2 correlations for a single timestamp for a single frequency channel. Now, as you know, there is no receiver can be built as monochromatic, so there will be a bandwidth also involved for any receiver, any detector you make. So there will be a number of channels involved. And in fact, we will come and discuss that more bandwidth you have, the better it is. Because you get more information, you can deduce more for the source from a wider band receiver. So as number of channels increase, as number of baselines increase, your computation number also keeps increasing. Okay, that has to be remembered. And you're observing this source as a function of time also, from rise to set. So more number of timestamp you receive, and with that low cadence, you have more data as a result. Okay. So definitely array which has just 6 dishes has much less data compared to GMRT, which has 30 antennas, compared to SKA, which is low, and at least which will have at least 128 plus number of antennas and tiles. Sorry, and so as we grow this number of antennas in an array, then the data rate also keeps increasing. Just we can skip this slide. Just a demonstration that as you looking at short baselines or lower U's, you have this widely spaced fringe pattern, and if you have a longer baseline, you have very fast varying fringe pattern. Okay, just sum it up. So the visibility, this is I is the response from the sky for a particular source in a particular direction, and V is the measured correlation. So if we do the math and there's some approximation about small field of view, we kind of deduce this to be kind of like a two-dimensional Fourier transform. Okay, and it is only possible just by imagining it's a small part of the sky we are imaging. So this is one approximation which is not true, but there are ways to deal with it, which will come later. For now, just keep in mind that the sky image is kind of a Fourier transform to the visibility we observe in the Fourier domain or the UV space. Okay. One important concept we told, this is how you link UVW values or the Fourier space to the baseline or the individual position of the antenna in the real space. This is a kind of rotation matrix which transforms the BXB by BZ to UVW, and what it depends in H0 is the hour angle towards the source of the center of the field. Declination is delta 0 towards the center of the field. Okay, so by this you can understand if the baseline is fixed, every other things is fixed, like the wavelength, the baseline, everything is fixed. Just if you observe the source from the rise to the set, what changes is the hour angle, right? It changes when the source moves from the rise to the set, from one part of the sky to the other part, and then finally sets. So for a single source with a single baseline, you will have multiple values of UVW. Okay, so even if you have a single set of antennas like 30 or 120 or 500, if you keep observing the same source over time, you can produce more number of UV spacings, and that's how you can fill up this UV space much more and create a better response to the sky by the interferometer. Okay, that is called what we say is Earth rotation synthesis. And that's a very powerful tool in radio interferometry, which we use very successfully to get much better images with more number of antennas, of course, wider bandwidth, of course, but simply by observing the same source over and over again through different parts of the sky. Okay, so here is some math produced by somebody in NRO, Urvashi, and I'm just showing the slides to see. So you have n number of antennas that produces n into n minus 1 by 2. It keeps on happening again and again. So this is the total number of combinations. And then if you have some number of channels, so these are with 1,000 complex values per second. So you can see how the data rate kind of gets computed as you observe a single field for a large number of time over a large bandwidth. Okay, so for VLA, it was estimated that it's about 1.8 petabit in size, plus 1 petabit per terabyte per day, kind of for the storage. So that's the kind of estimation for the VLA, which is just 25 antennas operating. Now, when you're doing computing, you have to remember that we observe this visibility as a function of time, as a function of frequency, but we have to make sure that data which we are recording are all good data, quote unquote. What do you mean by good? We have to make sure that these are not coming from, we are definitely coming from the sky, from outside the Earth, and not getting interfered with signals which are produced within nearby. So what are these signals which are produced nearby? I mean, if you're looking at different wavelength bands, there can be different things which are caused by mostly by human, and okay, for example, this is a slide from VLA. So here is this satellite downlink stage frequencies where between 1550 megahertz down to 1650 megahertz is satellites. There is this GLONASS navigation satellite. There is different other defense signals coming in. So one thing you have to remember that even though radio astronomers want to observe in different parts of this wavelength, the problem is that there is a current allocation for the RF spectrum. For different parts, different transmissions can take place. Now, because we are not transmitting anything, we're just receiving. So we are allowed to receive signals in any wavelength band, provided that signal is encrypted. So we cannot decrypt it. So we are fine to observe it, but we have to get rid of it because our science case is different, not to hear somebody else, but to hear from the cosmos. So these are basically what happening in the nearby communication within the Earth are basically noise for us. They're much stronger than the cosmic signals, and so this has to be removed from the data and basically what we say flagged or excised before we can proceed to make a reasonable analysis of the data. But that also takes a huge amount of computing. What typically happens is that the lowest cadence data is actually useful for removing this kind of RFI. And so that's a huge amount of data comes in through these correlators, and that then gets fed into these RFI excision routines, and then finally comes out with a much lower cadence data at the end, because once the RFI excision is done, we typically do not need such a high cadence and high time resolution data to begin our astronomical analysis. But yes, there are of course time domain sciences which requires data to be outputted at a very high time resolutions, like people who are studying first radio bursts, pulsars, for example. They need that, but typically for the continuum sciences, which I am mostly talking about, or cosmological signals, time resolution is not that critical a thing, except the fact that for this taking care of this RFI and something called Ionosphere, which will come at the end of the talk. Okay, how am I doing by the time? Okay. So as we collect data from two antenna, we know that it is passing through the electronics of each antenna. No electronics is perfect, so every electronic components will have some kind of a gain, which has to be calibrated and taken out of the system, because we are looking for the absolute flux of the observed from the sky. So unless we take away the gain, which can vary as a function of time or frequency, we will not be able to do a perfect reduction of what kind of source flux and property we are studying. But that kind of calibration also comes with a cost. It's of the order of n squared, or number of antennas squared, and that has to be also kept in mind while we are building up this cost budget for this computation for the imaging and calibration. So there's a cost for the editing of the data, there is a cost for calibrating the data, and of course, definite cost comes for imaging the data. Okay, so once you have done the basic calibration, then you basically go for doing the imaging. And to do that, you have to essentially follow a few steps, which we're skipping for now because of lack of time. You have to grid the data. Okay, so typically, as I said in the beginning, that the relationship between the visibility and the imaging is a two-dimensional Fourier transform. Let's stick to that for the time being. Now, everybody knows, I think, in this particular crowd, that a DFT, or a discrete Fourier transform, is much more expensive than a fast Fourier transform. So if you grid the data into the power n dimension, then you can actually apply fast Fourier transform. So you can make things go faster. So you have to basically grid the data. That requires a gridding convolution function to be applied. Hello? Am I audible?
Yes, yes, okay. I will go on.
Fine, fine. Okay, so it will apply a gridding convolution function, and then you do a FFT. Okay, so and then it keeps on happening. So this basically talks about the same thing. So you grid the data and you do an IFFT. You take a image, and so it goes through something called what we call it's a clean algorithm. A clean is, as the word says, clean. It's algorithm which was invented long time back, and it actually works pretty well. And many different versions of it has come to make it more appropriate, more sophisticated, and more to improve the performance of the clean algorithm better. But the basic premises remains the same. So effectively, you start with some model image. You have some priori knowledge, or you start with just the points to the field center, so just like a delta function. And you slowly, what you do is deconvolve the sky, deconvolve the model. You take the model, you convolve it with the PSF, or the point spread function, which is the kind of the array beam or the response of the array in the Fourier space, and you convolve that and you remove that from the actual data. So that's data minus the model, and you look at the residual, and you then do further processing to essentially deconvolve out this array beam from the data completely. So you go through a couple of iterations in this particular process. Okay. So you make a better model, and then you take the better model, and then again go to the same space and do this till you get a residual which is acceptable, meaning which is kind of the residual you should get from the time of the observations you have done. So remember, on top of this, which we are not mentioning here, every observation is related to some kind of a noise, the noise which is coming from the electronics of the system, and the sky coupled with the beam, primary beam of the antenna. So if you observe for certain amount of time or certain number of samples, this typically, if it is not systematic dominated, then this typically goes down a square root of number of samples. Okay, so if you have observed for a finite amount of time, you definitely are restricted to certain RMS value or residual noise in the data. So once that residual is acceptable to you, you stop this process of deconvolution and you say, okay, whatever we have got is finally acceptable, and we move on and look at the data as the final result. So it is a one step. So this is like the PSF of the beam. You convolve that. This is the dirty image you get, which is basically without the deconvolve. And so you have to clean that to kind of get back to the original portion. So that's one step of basic calibration and the imaging which has been done to get to the image from the sky. Now, typically, if you're looking at the visibility, typically it comes with a bunch of gains in front. Some of them can be dealt with before the imaging. Some of them has to be dealt with in an iterative manner with the imaging followed by another calibration and then again another imaging. So this is called what we call is self-calibration. Okay, where you calibrate the data by the best known possible model which is created for the data itself. It's a bit complicated for now. Just let's keep it there, and if you want more information, you can write to me or we can talk later offline. So just to show you the effect, because I'm not doing very great with time, this is what happens with the uncalibrated data, okay, and which happens with a little bit more calibration, okay. So sorry, this is like a calibrated source or a point or compact source. This is the uncalibrated version versus the calibrated version. So you can see the source has been actually reconstructed properly, much better by this imaging and deconvolution as well as the calibration steps followed. It's the same thing if you're looking at a supernova. So I think you are or extended source in this particular case. Sorry. So this is the uncalibrated image. And if you do calibration properly, you will be seeing something like this better. These are all examples taken away from synthesis imaging workshop by Inario. So you can also visit the sites and take a look at that. Now, you have to do this probably after one round of self-calibration. So if you do it multiple rounds, you probably will end up being the first image being this to the final image being this. This is again Cygnus A and the classic FR2, which we've shown in the beginning on also. Okay, so that's kind of the way we proceed. Okay, now as I said that these are all done for some bandwidth, finite bandwidth, and for some timestamps. Now, actually, if you make the bandwidth larger, you actually can look into a much higher UV coverage in the UV space, and that produces much better image because you are actually looking at much wider data. But that also puts certain constraint on how do you process the data. So there are ways to tackle large bandwidth data because you cannot ignore a couple of more intricacies which results for that. But anyway, when we're talking about interferometers like SKA or even GMRT now, it has a wider bandwidth, the upgraded version of the GMRT, and these algorithms, the multi-frequency synthesis algorithms are much required to process the data over a wide bandwidth. So this is a one-page summary of kind of amount of computation involved while you're doing each and every step. Hello. Hello, can you hear me?
Yeah, Abhirup, we can hear you. Please carry on.
Okay, fine. So if somebody
some background.
Fine. Okay, good. That's okay. Okay. So this is a one-page summary of what kind of computation is required for each particular. Sorry. yeah, each particular step. So you can see that is if you're looking at the data, that's typically n square, where n is the n antenna square, number multiplied by number of channel, multiplied by number of polarization, which we haven't come yet. So typically polarization is IQ all 4 Stokes. So it is essentially it is RR, LL, and RL and LR. So there is a two polarization, right and left, and then the cross polarizations. Okay, so there are 4 in total, and then total number of times. So that is total number of data volume which is coming, and then how it kind of each and every step, how does it contribute to the computing expenses in each step is kind of summarized over here. This is a typical pipeline which we follow when which is doing through something the most widely available software called CASA, or Common Astronomy Software Application, and it is done by maintained and developed by NRA, and it is also going to be useful for analyzing SK data in future. So that is typically what we did. So we have observed data, then you have sub steps to assure the data is quality is actually good. So you remove the bad quality data from the rest, and then you only deal with data which passes through this quality, and then do what we call initial rounds of calibration, transfer the flux and the phase, and then finally start doing what we call imaging, and then couple of rounds of self-calibration to finally come to the images. Now this range of I will come to that in a bit. Now this is the right point. So this, when we say calibration in the previous slides, we actually talked about calibration which are not direction dependent. Now so we mostly talked about direction independent calibration. This term also came to you while Neeraj's talk. And what happens is typically when you derive let me go back a couple of slides. Yeah, when you derive this kind of gains, it's actually driven towards the phase center or the center of the field. Okay. However, there are certain effects like the effect of the primary beam itself, and something like ionosphere, which we'll talk in just a second. They are actually varying across the field of view. Okay, so if you have a particular antenna, it has a particular field of view designed by its primary beam pattern or radiation pattern. Okay, so so basically across the beam, by doing self-calibration, it is only deriving one solution, which is towards the field center. Okay, however, there are certain corruption terms where this is not sufficient, and you have to involve more terms, more directions, for example, to make it work better, because ionosphere or primary beam can actually be changing across this field of view. And so to correct for them, for more high sensitive observations, you need to do something called a direction dependent calibration. Okay, so because one of the proponent is the ionosphere, so we come to that. Ionosphere is what is between us and the sky, is the atmosphere. And when we're talking about radio frequencies, lower radio frequencies below 1 gigahertz, the part of the atmosphere which is most bothering is the ionosphere, or the upper part. When we're talking about frequencies which are higher than the 10-15 gigahertz, what affects us is the lower part of the ionosphere, or the troposphere, or the water vapor levels, and all these things. So again, a fantastic cartoon. This is the cosmic wave background, microwave background, and then this is the signals from the dark ages, epoch of ionization. Oops. And then you get the signal coming through the extragalactic foregrounds, galactic foregrounds, and then it passes through something called ionosphere. So what is ionosphere? It is an extended structure going from a few tens of kilometers up to a few thousand kilometers above the Earth, and it modifies the phases. It has different effects which will come in a second. So it has, at least the broader sense, it causes refraction. So it actually appears like a convex lens. So in a particular frequency, you're seeing more part of the sky than this. And it also attenuates signal. and completely attenuates below some frequency like the plasma cutoff frequency, which is typically around 10 megahertz. So if you're doing science below 10 megahertz, you cannot do it from the ground. You have to do it over space. And but still, even if you're doing science below 200 megahertz or so, ionosphere becomes a very significant devil at this frequency, and you have to deal with it. And the one way to deal with it will be to do this direction dependent calibration. So this is our favorite GMRT, and you can see this is a low for observation, by the way, not a GMRT observation. So what I'm displaying here is that 2 nights observing the same field of view. So same bunch of sources in same parts of the sky observed by LOFAR. This is a quiet day on the left, and you can see something is moving at the background, but not disturbing the sources at all. But the same field observed in a terrible ionospheric activity, and you can see the ionospheric disturbances or the traveling waves, traveling ionospheric disturbances are actually making the sources appear to move. So these are the snapshots in every 30 seconds. So you have to make the image like over few tens of minutes or maybe more. So if you actually collate all this data and make it, these point sources or the so-called point compact sources will appear to be diffuse emission kind of a thing. So you're making a wrong judgment in that sense. So you have to calibrate for this, and for that reason, this is a single field of view. So the ionosphere over here is not same as ionosphere over here. So you have to do this calibration, which is direction dependent. So we have done some observation with UGMRT at 300 megahertz or so, and observed the sky, which very get dynamic range, and significant amount of RMS noise have been reached. So this is another one at the same frequency, but a different field of view called Lockman hole. So you can see these 3 different areas where the one which is more noisier are the direction independent calibration images, and one which is less noisier are the direction dependent calibrated images. Okay, so you can see that the difference between the direction dependent effects being calibrated versus not calibrated, and this effect actually grows away from the field center as you move from the field center towards the outskirts. So as you see, the things which are near the field center are more or less okay, but as you move away, things starts behaving in this peculiar manner. So that's motivating that for a telescope like SKA, and if you're doing typically very ultra-sensitive experiments like the epoch of reionization and cosmic dawn, you need to employ this kind of algorithms. So we come to the telescope which we are all talking of, the square kilometer array. And the particular change in the regime is this particular factor. Look at this. This is something which goes from 50 megahertz to 350 megahertz, quite in the little bit lower to what GMRT can go so far, but it covers the band which GMRT is very well active in. However, what changes is this is the data rate, 157 terabytes per second. Why? Because you have quite a bunch of antennas in this particular thing. So this number of total number of antenna combination, the bandwidth, the time you're observing, all this thing makes the data rate go 157 TB per second, or 4.9 zettabytes per year. Okay, compared to that, the higher cousin of SK1 low is SK1 mid, which will be in South Africa. The data rate is not that crazy, but still crazy enough for the current time being. It is 2 TB per second. We observe GMRT, you upgraded GMRT for about 6 hours. We feel 1 TB kind of in the current with a very high time resolution. Okay, so this is way up there. So it's complete change how you store data, how you process data, how you and it was told by somebody that previously we used to be very conservative for proposing something new because telescope time is very precious. But here the regime is different. Here storing the data is much more costlier than actually re-observing the data itself. Okay, so it's kind of a regime change between what we are doing right now and what we are going to do in about a decade or maybe less than from now. So SK1 is definitely is going to be much more sensitive than UGMRT or the current JVLA. We don't have the NGVLA plot over here. Even for low and the mid band, I think that's a thing. This is the low antenna, how it looks. This is kind of a one single tile. So it's a bit different concept than a dish like GMRT. So you have single dipole and you make a composite of such 256 such dipoles, and each of these stations behaves like a single dish, okay? And you have 512 of such dishes. So you're going from 30 antenna combinations to 512 antenna combinations. So you know data rate is increasing, no wonder. Just to show that how the data rates kind of evolve from here. So this is from the basic input to up to the where the imaging does, and finally how it is stored. Again, some numbers over here. I think I have 10 minutes. Okay, we can go a little bit slow. So if you have the EOR like experiment going on, if you're looking at 5 squared degrees and about 1.7, this is, yeah, 0.17 million channels. You have kind of 500 TB UV data sets and images of 3-dimensional up to 1.5 TB. So this is basically a breakdown of what we saw in those info slides. How this is processed? Of course, we have not finalized how the SK data will be processed because this is still under discussion because we have still time to go. But I think there are several discussions groups, bodies which are being formed. One is called the Science Data Product or SDP, who are taking care of the how to raw data will be taken and processed and what will be the observatory deliverable data output products, which will be then be distributed to the PIs or the participating nations, and how will they be stored across the globe. That will come in a bit. But there are other groups which are discussing how to store this data, how to distribute the data over the entire globe, and how to affect this processing. So somewhere in between in this SDP group is what is going on. This is a slide from the LOFAR, which is kind of similar to what SK1 low will be doing, kind of. And this is, you can see how this is done in their case. It's taken from my XCon presentation from the LOFAR group. And we take a lot of raw visibility, do the RFI excision by some routine called AO flagger, and then you correct and do bunch of this in between steps, and you are doing this direction dependent calibrations right out here. Okay, so few numbers is that when you're doing the imaging, it is fine for SK1 like antennas, telescopes. But when you're doing EOR like experiment where you really need data to be very high precision calibration, your direction dependent calibration takes about 95% of all the resources. This is exactly coming from the same report made by the LOFAR group in the XCon, and I'm just copying from there. So 95% of the resources goes in direction dependent calibration, and imaging is okay, it can taken off. This is kind of a regime change again, because initially the most of the computing cost was imaging based. Now it is going into the direction dependent calibration, no wonder, because depending on how many number of line of sights you want to calibrate, this will actually grow. So coming to the part where, so you collect data from the telescope, you process it by this initial SDP stage, which is the science data product stage. You make something which is delivered by the observatory to the PIs, but then you come to how will you store this data for future use. So the currently the acceptable model is there will be regional science data centers across the all participating nations, and there will be stored data in multiple redundancy distributed across the SRC. In fact, something like a proto SRC is started to get built. This is a snapshot of that, who are currently participating across several science data challenges which are designed by the SK office. So the second one just finished, and the results were declared yesterday, or will be getting soon. I think the idea was to have the teams across the globe participate in this and actually reduce their data in what one of these proto-SRCs when you get time and see how it works. So I think there's a lot of computing and resources required, not only just to get the science data product done, but also to store the data and differentiate between, what is a good data versus bad. So a lot of applications for parallel computing, GPU-based computing, and applications of ML, machine learning algorithms to classify data is on way. So I think stay tuned, and I'm happy to discuss more on this. I guess I am on time. Sorry for rushing to the end because Panjan said there will be a discussion at the end. Okay.
Yes, thanks a lot, Abhirup, for this wonderful overview of the very many challenges that we face in reducing this data. And finally, we get a very nice image. Questions? Participants, please raise your hand. We can have a few questions before we move on to the next topic. So Abhas Pradhan, please unmute yourself and ask your question.
Yeah, good afternoon. Thanks a lot for the insightful talk, sir. So we talked about how we did a directional calibration.
Yeah.
But how do we do a time calibration? Because the signals coming from a source must be reaching the dipoles differently, and also to the data center themselves from the communication as well. So how do we calibrate them?
No, so you are right. Something I think we just went over quickly. There's one sense of time is there if you're looking at the slide currently. So as the signals are coming from the far field, from the astrophysical sources, what they do, they're emitting spherical waves, right? But if it traverses infinite amount of distance, it becomes plane wave. So if both of the antennas are looking at the same plane wave and you are sampling the same wave front coherently, then there will be a time lag between the signal reaching here faster, if this is the direction, which is this particular antenna number 2 ahead of time than that antenna number 1. And so that is basically geometry based. So if you know the direction which you're looking and you know the B, so you can actually compute this B dot S and convert this to a geometric time delay and correct for it, so that you can actually doing this correlation coherently. Okay, that's the time correction we do to get the fringes in it. Okay, sorry, we missed that because it's difficult to cover all the things in the same.
Yeah. So the thing is this calibrated beforehand? Is this correction determined before, or there is a real time correction where we timestamp?
This is inbuilt because you know your array, right? And you know your array, you know the B's, the spacing, exact spacing of the between antennas. So only thing you need unknown is that for that particular timestamp, where are you looking, right? If all the antennas are looking in the same direction, that is also known to you. So you can basically correct for that. Okay.
Thank you, sir.
Shumit Banerjee, please go ahead next.
Am I audible?
Yeah. Yes, go ahead, please.
Good evening, Abhirup sir. Thank you for the lovely talk. My question to you would be, how does any radio telescope array distinguish between the actual radio source coming from the astrophysical object and the ambient radio noise that is all over the place?
Yeah, that's a very good question. That's what basically we said you have to localize it in some time domain. So for example, when you're looking at RFI, okay, so here, yeah, so here you can actually locate it in the frequency domain. So typically what is coming from the sky, unless it is a spectral line, in that which case you'd actually know which line it is and which frequency it should be. Typically it is very flat, slowly varying across frequency, not as fast varying as this stuff. Okay, so you can localize it in the frequency. sometimes you can localize it in time. Supposedly you are looking in this time frequency plot, just like we are looking here, down here. If you see only a particular timestamp is problematic, looks like giving you higher power than the others, you can actually understand this is something which is not or cannot come from the sky. Although it is partly not true, because you see these transient events in the sky, which we are now very fascinated about, called FRBs and other transients, and that too are like transients, meaning by the name, they're on for some particular timestamps and off most of the time. So, but typically their strength is not that high. So by strength also you can understand if it is man-made versus if it is coming from outside. So yeah.
Thanks, Sumit. Okay, now maybe the last question, a quick one. Prayush Kumar, please unmute yourself and ask the question. Prayush, go ahead, please.
Hi, Dr. Abhirup. I have a question. So keeping aside the question of data storage, if we look at only the analysis of all the data that each of the individual receivers are generating,
right?
Are the algorithms being used for the analysis? Are they CPU bound or communication bound between different CPUs that are being used to analyze them?
If I understood your thing, is it enough parallelized? That's what you're saying?
Yes.
Okay. So the quick answer is it has started to. So some of the jobs like this RFI excision, they are completely parallelized. They can be, because you don't need to do one thing with the other. But some others, like the imaging, they cannot be essentially completely parallelized. Okay, there has to be some crosstalk, because ultimately you are doing. So depending on which are you doing, like this direction dependent calibration, you can also do parallelized in some sense. So efforts are being made to make it parallelized, and as well as to make it GPU friendly. And those are going on. Even there are some benchmarking currently being done, how to use cloud computing on AWS and still get it done. So variety of things are underway. So I think, but yes, I mean, technically these are memory heavy, typically very memory heavy than CPU heavy, because data rate is so high. Yeah.
Thanks, Abhirup and Prayesh. Maybe we can take this discussion a bit later on. We are pressed for time for the panel discussion.